Hey, good evening, everyone. So today we'll be doing section 7.2 on trigonometric integrals. This is just integrals that do involve trig functions. You've already seen this before, but this will be a little bit more advanced than what you might have saw if you took Calculus 1 and you saw this, a sine over a cosine, which is just tangent, right? So that's why it's really important to know these trig identities, and that's what I want to start with. Make sure you're familiar with these. These three here, they call those the Pythagorean identities. You can tell these two almost look the same. 1 plus tangent squared equals secant squared. You're just going to make sure we're really familiar with them. Sine squared plus cosine squared equals 1. 1 plus cotangent squared equals cosine squared. Something else is going to emerge in this section, and for the remainder of this course, these power reducing identities become important. These allow us to do the integral of cosine squared of x and the integral of sine squared of x. And so all we have to do is use these power reducing identities, then it's easy to do that. We'll just involve a u sub in there. I also wrote down, we know about sines and cosines and their derivatives. Something to play a part today that's important. We just got to be very familiar with, hey, what's the derivative of tangent? Secant squared. So what would be the integral of secant squared of x? Tangent of x. Well, I wrote it this way. I wanted to just stay consistent with what I was writing here. And the integral of cosecant squared of x would turn into a negative cotangent of x. So those are going to become the play part today, right? So in terms of this derivative, I can get that, or a positive become a negative, right? So hey, I'll start out with a problem. Let's see. This is from section 7.2, and this is actually like problem number 3 from the textbook. Sine 9 x cosine 5th x dx. Actually, the textbook used theta as the variable. I just changed theta to an x for this first problem. The problem had a 7 to the 7th power. There are limits to integration. I'm going to use the same ones I saw in the book. They went from 0 to pi over 2. So it's a definite integral. In the end, we'll substitute these numbers. So definitely, the substitution rule is going to play a part here. Do you all agree, like the derivative of sine of x is cosine of x? The derivative of cosine of x is negative sine of x, right? But these are high powers. And so we're looking at this scenario, it's like somehow we've got to use something over here to substitute so we can make the u sub work. So the goal, what's the goal when we have, sines and cosines in a problem like this? You just got sines multiplied in terms of a product. Your goal is to make one solo lonely trig expression. So I'm going to say when you have, I'll say with sines and cosines, you want to get one lonely either sine or cosine. I'll write trig expression. Or trig function. You want one lonely trig expression. You want to rewrite this before you start and just get like a lonely sine of x. Or a lonely cosine of x, and then everything else could be in terms of the other trig function. So let me just be clear here, and we'll work it with this problem. If you get everything in terms of sine of x, and you can have numbers in there, but then you'll notice at the end, maybe somewhere in this expression, you just got this little cosine of x. Right? Or you get everything in terms of cosine of x. You got cosine to the 9th power, cosine of x to a 5th power, etc. But then you have this lonely sine of x. And that's going to allow us to do the substitution rule. Because the whole idea when we do a substitution rule, doesn't something get divided? And so that's our goal. So we're trying to get this what? One lonely trig expression, maybe sine or cosine. So let's try to start busting this study up. I'm going to focus on that lower power. I'll explain that in a bit. So even before I start, I'm going to go 0 to pi over 2 sine of 9th x. How about I just do this? Cosine to the 4th x times cosine of x. my goal is complete. And I'll get this out of the way. I just want everybody to focus on this. I got that one lonely cosine of x there. Does anyone see it? Now with this, I have to make sure everything else is in terms of signs, so I need some help. And we won't use the power reducing identities yet. There's a way I can rewrite this cosine of fourth of x. So let's look up here. What do we got here? The relationship between sine squared of x and cosine squared. Sine squared of x plus cosine squared of x equals 1, right? So this, we'll start out with, and I'll get this out of here. We accomplished our goal. I got this one lonely cosine here. This is even. So I'll leave this sine of 9x. I have not performed the integral yet. We're just playing around with the trig identities. Isn't this cosine squared of x squared? There's that lonely cosine of x dx we want. Just leave that there. But can I do this? So now I've worked it down to where I can use what? This trig identity. But that was I wanted to somehow get the expression set up so I can actually use that trig identity, sine squared of x plus cosine squared of x. And so I want all sines and this lonely cosine. So I'm one step away. How can I change it? Using that trig identity. And you might write it on the board. How can I rewrite this? What is sine squared of x equal to?
1 minus sine x squared.
I love it. I'm just going to write it here. Sine squared of x equals 1 minus cosine squared of x. That's what we're saying. I'm going to put that right there, right? Sine squared of x equals 1 minus cosine squared of x. What does cosine squared of x equal?
1 minus sine squared.
Just rewriting that identity, and that's going to go right here. Boy, now we're going to roll into our u substitution. But before we do that, no rush. I want you to stare at this carefully. There we go. Look at this setup. There's that lonely 1 cosine of x. With not cosine squared, cosine cubed, or cosine to the 4th, just cosine of x. Everything else is in terms of sine squared. Or excuse me, in terms of sine of x. Just sine of x raised to the 9th power. This is sine of x raised to the 2nd power. Hey, and before we get lost here, I want to make sure, when they write this notation, you agree it means this? Sine of x all squared. It's just an easier way to write it. Limits the amount of parentheses we have to write down. Same thing with sine of that 9x. That means sine of x raised to the 9th power. So, it's ready. This thing is ready. Guess what we'll let u equal to? Sine of x. We're going to let u, it's a u substitution. We're going to let u equal sine of x now. So what letter can I put right there? U. What letter will go right there? U, 1 minus u squared to squared. But the best thing about this, what's going to happen to this part? You notice you're going to see that just slip away. Because when we do a u sub, it's u equals sine x, and then we differentiate on both sides with respect to x. What's du equal to? So I hope this goal is becoming more clear. Where you go, that's why we're doing that. I'm going to now do a u sub. This is going to get replaced with the du. Everything else is going to be in terms of u. U to the 9th. 1 minus u squared. Squared. You're gone, replaced with a what? Du. So bye-bye, you're just a what now?
Du.
You're du. But this u is going to replace every sine of x. So this is u raised to the 9th. 1 minus u squared squared. Uh-oh. I can't put 0 in pi over 2. How do I change those limits? I think a lot of people, I noticed a lot of hands in this class like to change limits of integration. I think I'll do that. Can we do that? What is the sine of 0? 0. I'm changing the limits of integration because I changed the variable to u by the u sub. What is the sine of pi over 2? 1. Good. Actually, I got better. So we're just going to finish up this integral. This is something you've seen in Calc 1. We do have to expand this, don't we? Now let's expand that. 1 minus u squared squared. You know, FOIL. So if you expand that, 1 minus u squared times 1 minus u squared, I get 1 minus 2u squared plus u to the fourth? Everyone okay with that? By foiling this or expanding the 1 minus u squared. And then distribute. So this integral symbol, what, step 1, 2, 3, 4, 5, 6, 7, still sitting here. You'll see this is common in this section. Just kept playing around with this through trigonometric identities. I get u to the 9th minus 2u to the 11th plus u to the 13th du and integrate these. Find the antiderivative, substitute 1 and 0, subtraction, right? What's the integral of u to the 9? U to the 10 over 10. What's the integral of 2u to the 11th? That'd be u to the 12th over 6, right? All right. And u to the 13th? U to the 14 over 14. And plug in 0, 1. Since we changed the limits of integration, I think this will be easier, right? Okay. Anything weird?
No.
Oh, cool. You can get that common denominator and just subtract these. Many students just like to use the calculator here. Do that math right there, and then you plug in 0 and you get zeros, right? That's not a very big number, but it's a little bit more than 0. What is that? 1 over 210? But this was the key step. I'm going to box this off. If you want to box it off in your notes too, to say that was the setup you were trying to get. Somehow, everything in terms of one of the trig, like sine, all over the place. Sine to a 9th power, that's fine. 1 minus sine squared of x, that's fine. But then you had this lonely, I call it a lonely cosine of x dx. I could have done the reversal. Do you all agree? I mean, there really is another way to do this problem. I could have got everything in terms of cosines, and then the lonely sine of x. So I'll go back, just looking back, and tell you the reason I chose this. When I see two odd powers, I tried to break up the lower power because if I took that higher power, do you agree when you got to FOIL something, it's not too bad? But when you got to expand something to like a binomial to the third power, it gets really long. That was my reason. I think it would have saved a couple steps in math. Awesome. Hey, I want to do another sine cosine problem. But this, you'll notice you might have to do a little chain rule over here, right? That's all. But you notice both of these were odd powers. So I really had an option which one to break up into an even and an odd to get the lonely. But I chose the smaller power to break up. I just thought it was easy. You're going to notice in this next example, one of the powers, it's got a sine and cosine. One of the powers is odd, one of the powers is even. So we'll talk about that. Can I raise? Right. Hey, here, let's look at another sine.
No.
Oh, still going? Yeah, you bet. Here, go ahead, Jessica. Thank you.
You're so slow, Jessica. Keeping the class behind.
Good job.
Thank you. I got it now.
You got it, Jessica. All right. Hold up. Sine squared of pi x cosine to the 5th of pi x dx. Well, it looks like, and this one's an indefinite integral. It looks like something very similar. I do notice one of the powers is even, one of them's odd. So in this case, we're kind of forced to break up this one to get the lonely trig function. Do you agree? We're going to leave that one as is. But I'm going to write this one right here as a cosine to the 4th pi x and then a cosine of x. Cool. All right. This what happens. If you notice one of these is even and one of them's odd, the one you're gonna break up is the odd power. Cool, Katie.
So even if it's squared, like sine squared pi of x is, you wouldn't swap it for the true function as is?
That's right. Now, I know you could have, there's other ways to do the problem. That's the beauty of math. Like, you can keep playing with this thing. As long as you get that goal of what? Everything in terms of sines and then lonely cosine vector, you're gonna get the problem solved. So really good point. I just don't want you to get boxed into something you have to do. You can play with that thing. I heard you saying, well, I can make this 1 minus cosine squared, right? But because it was an even power, I'm like, you know what? I can just leave that as is. This allows me to write cosine of x, wait, cosine of pi x, a lonely one. There's that, I'm gonna call it the lonely cosine of pi x. But now I have to write this as what? Cosine to the fourth pi x. Very good. Now, Katie, can you help me out? Help me get that in terms of sign. We're gonna leave this one. This is gonna stay. Okay. We're trying to get everything in terms of signs. Leave this.
It would just be cosine squared and then everything squared.
Okay, she says it's cosine squared, all squared.
And then it would become 1 minus sine squared.
And you're rocking. Way to go. You are rocking. Let me make sure that everyone can see that squared right there. She's a step away. Leave the lonely. There's that lonely cosine pi x. Leave that in terms of sine, but now we can rewrite this as 1 minus sine squared of x. And it's u sub time. It's u sub time. Okay. Boom. That's what we wanted. The rest of this problem at that point is smooth sailing. Because you got the lonely cosine pi of x. Everything else is in terms of sines. And what do I let u equal to?
Sine pi x.
There you go. Let u equal the sine of pi x. Only difference between this problem and the last problem, why I wanted to do this with you, number one, we do have to apply chain rule. I want people to see that. Number two, that doesn't call it a big problem. Number two, I want you to see what happens, Katie, one's even, one's odd. I broke up the odd to get an even with that lonely trig function. That's how we always try to handle it. All right, what's du? Cosine of pi x, right? That's all I gotta write? Did I screw up? Did I screw up? Yeah, this one I want you to be careful of.
Forgot the pi.
The derivative of this, right? And this is, I'm doing differentiation derivatives, chain rule. The derivative is cosine of pi x times up pi. I'll squeeze in there. Ooh, question, go ahead.
Can you take out the pi in the beginning of the
No,
integral?
I'm with you. Think of this as untouchable. They call it the angle or the argument. The only way we can play around with that thing is like do trig identities. But we still can't do it. But this pi, look at that guy. Now that one you're going to be able to stick out in front. Let me just do one more step. Because what we're trying to knock out is the what? This cosine pi x dx. So I'm just going to think of this as divide a pi on both sides, right? 1 over pi du I can use to substitute for the cosine pi x dx. But boy, yeah, this one, let's stick that 1 over pi in front. Because that one came out as like a coefficient. But you're right, untouchable. Untouchable, untouchable. Same thing goes with like log expressions, like log of 5x. We can't take that log, the natural log of 5x. That 5x is an argument. Are you ready to substitute? Let's do it. That's replacing the cosine pi x dx, pi by lonely trig function. And then u is going to replace every sine of x. Oh, excuse me, every sine of pi x. U will replace every sine of pi x. The 1 over pi here. Here. Get it out of the way, right? Du. Is that okay with that? 1 over pi du replaces the cosine pi of x dx. That's just u squared. And now you have 1 minus u squared squared. Not bad at all. And then the du. I might as well push it further here, right? Yeah. Oh, well. Put this next to it. Sounds oh, we got to expand that. What's that expand? When I say expand, I'm talking about with these square FOIL. What's that? 1 minus 2u squared plus u to the 4th. Distribute. Okay. 1 over pi. U squared minus 2u to the 4th plus u to the u to the 2nd times u to the 4th. Just be careful. U to the 6th or u to the 8th? 6. We actually add the exponents. So you do that a lot in this section, you'll notice. I just want to review that. You go, oh yeah, when I multiply this to this, we actually add the exponents. It means you got 6 u's here, right? All multiplied together. All right, what's these integrals?
1/3 cubed.
U cubed over 3, 1/3 u cubed minus
U to the 5th power, or 2 times U to the 5th power.
boom, and u to the bless you plus c. I want to make sure this is separate. I want to get out of the way. Get this out of the way. You're off here. Hey, am I done, or is there something else I got to do? Because this was an indefinite interval. Yeah. Everything originally is in terms of what letter? X's. And because this is an indefinite integral, I have to do my last step and resubstitute. Every u, I'm just going to resubstitute with a sine pi of x. Rewrite everything I got there. Keep the 1 over pi, but every u I replace with a sine pi of x. So this final answer becomes 1 over pi, 1/3 sine pi x cubed minus 2/5 sine pi x raised to the 5th. Yeah, of course you can use the other notation if you prefer. We put the 3 right here and the 5th power right there. You can do that. I just want to point out this is another way to write these. True? That's what it means. And what do you got here? Plus 1/7 of sine of pi x raised to the 7th power. But yes, once again, you can use this original type of notation here. Just a different way of writing it. This is the final answer. The antiderivative. Want to give more time to copy that. Hey everyone, super job so far. Notice we haven't used these yet, have we? Although I've seen sine squared and cosine squared come up repeatedly so far today, but we haven't used these. You'll go, when do I need that? It'll be a specific case, you'll see. It was all through this one. When you had sines and cosines in terms of a product, in terms of different powers. Take your time. Okay, next problem, very similar. What if you have tangents and secants? Guess what's going to be very helpful? This one right here. Okay, so once again, you know, what if you have secants and tangents combined in a similar scenario? Okay. Number 29. From section 7.2. They write tan cubed of x secant of x. Tan cubed of x, or tan of x cubed, times secant of x dx. We're taking the integral tan of x cubed secant of x What's our goal this time? Before we wanted one lonely sine of x, or we wanted one lonely cosine of x, right? What's great about tangents and secants, what's the derivative of secant of x? What's the derivative of it? Secant x, tangent x, you better one. This is the derivative of secant of x. Y equals secant of x, the derivative is, y prime would be secant of x, tangent of x. So one great goal is to get one lonely, not just secant of x, this thing. I want to be thinking like, if I can do a u equals secant of x, then the du will equal secant of x tan x dx. So I want to get one lonely secant x tan x somehow. Man, if I can just make that pop up somehow in my integral. Before I start working the integral, we're going to be fine because I can let u equal secant of x, and it'll knock out that other what? Secant x tangent of x. So does this make sense, everyone? I'm not saying just get a lonely tan x. Get a lonely secant of x tangent of x. Ooh, go ahead.
Did you rearrange that 1 plus tangent squared x to tangent squared x equal to secant? Or no, I'm sorry. Split that one, the odd one, right?
Split it up. You're already onto it. I like it.
Yeah.
So I'm going to do that. You're telling me he's rolling with this problem, and when this is our goal, get this lonely secant of x tangent x, and you go why? Before it was a lonely sine and cosine. This is the reason. What's the derivative of secant of x? Secant x tangent x. It'll knock that thing out, and everything else will be in terms of secant. Okay? So let's go with this, and I like you started with this, right? You said I can rewrite this as tangent squared x times a. You have accomplished the goal. There it is. You got it in one step, didn't you? Cool. But one more thing we're going to do. We want to get the one lonely secant of x tangent x. We want everything else in terms of secant of x. So, leave this though. There is that one lonely sitting at the end. It could be anywhere in the integral, but there it is. But what can you do with this? Can you rewrite that in terms of secant?
Would you rate it secant x squared minus 1?
That's right, and you just use this identity right here, right? So tangent squared of x equals secant squared of x minus 1. Said the same thing. I love it, David. Andrew and David, perfect. I'm going to do this. Put a parentheses, put a squared, and rewrite this as secant squared x minus 1. And there's that lonely tan x, secant x, dx. One lonely secant x tan x. Everything else is in terms of secant of x, right? Nice.
Why do you square it? If it's already tan squared x equals secant squared.
Oh yeah, right here, you're the best. So this tan x, secant of x, we got tan squared x. I was thinking I was tangent to the fourth. And kind of thank you so much for spotting that. So when he corrected me right there, he said, that's just secant squared x minus 1. There wasn't no square here. Like tan x doesn't equal secant squared x minus 1 is what he's saying. But thank you. All right, we accomplished our goal, right? I guess I can put the real smiley face here in terms of secants, tan secant. All right, what are we going to let u equal to? Put it over here. Got our goal. Kind of thanks again. Go off to the side, and this is what we'll do. U equals secant of x. Du equals secant x tan x.
What about the dx?
And I'll put the dx there right here. Thank you. And this becomes
U squared minus 1.
square minus 1. What happened to all that? Du. So let's see how to go u squared minus 1. U cubed over 3 minus u. This is an indefinite integral plus c. I'll step away. Am I done?
No.
Good.
Secant x and
Very good. Indefinite integral. We did do a u sub. So I'm going to go back. Resubstitute, right? U is secant x. You can do this notation if you like. Or use the parentheses. There's the antiderivative. Man, outstanding. Hey, the beauty of mathematics is there's not just one way to work problems, right? Our goal was saying with this problem, if I see secants and tangents, I'll get everything in terms of secant and have this lonely secant x tangent, just because of differentiation here. But what's the derivative of tangent? Secant squared of x. So if you really think about it, everyone, if you're like, man, if I can get everything in terms of what? Tangents, and then get a lonely secant squared of x, that's another way to work the problem. It wouldn't have worked here though, I don't think. I don't see a secant squared, do you? But I just want to point that out. You can say, wait a minute, there's another way to work some of these problems where there's a tangent with a what? Secant. There could be another way to work the problem where you go, I'll get everything in terms of tangent, but I'll have a lonely secant squared x dx that would get knocked out, right? It'd be very similar to what we were doing before. You notice here it wouldn't have worked, right? Because look, if we let u equal tangent of x, the derivative is, like we said, secant squared of x, and there's no secant squared of x up there, right? You're like, well, I could have got this one. Well, yeah, but it's not lonely. It's with that minus 1 in there. So, this next problem is going to look just like this. Oh, here we go. Tangent to the fifth x. Secant to the fifth x. But if you don't mind, I still think we should try this. Let's try that first. Can we take this thing, get a secant x, tangent x, and everything else in terms of secant. Secant, and a lonely secant x, tangent x, dx, so that you'll have that. Well, what could we do?
You reduce both of those to begin with.
Okay. So what you would have,
Tangent to the fourth x.
tangent to the fourth x, leaving you a tangent x to go with it. Secant to the,
Fourth x.
and now you have a
Tangent x.
great start to the problem. Outstanding. So he's almost there. You all like that? There's that secant tangent. The order doesn't matter, we know that. Let me hide this. Can you get all that in terms of secants? That's what we need. Leave that, of course. How can we play with that?
So